Okay, so this is the last bit of new information that we need to kind of have down in preparation for the test on Thursday, right? Tomorrow will be a review day. Thursday will be the test. Okay, so this is the last little bit of new information. But as you can see, there's some trickiness that can kind of go on here. I mean, you think to yourself, how hard can it be just adding up the same number, or adding up numbers over and over again with a pattern or something? But it gets a little tricky. So I want to take the quiz for you. I mean, no. I want to see what you have to do. What you know. Yes, I see. But the purpose.
Yeah. Is the microphone on?
Everything's on right now. That's right. The walls have ears right now. Okay. So, people need to watch the channel in order to like and subscribe it, though. So Oh, thank you. Fine. I appreciate it. Anyway, geometric sequences and series. Okay, so that's what we're gonna look at today. Again, I'll talk about a geometric sequence first, and then we'll talk about the series. Okay, so again, this is a named sequence. There are many sequences that we can come up with, right, that are not geometric. There's many that have names that we're not going to look at. We've talked about Fibonacci just briefly. We learned arithmetic yesterday. That's when you add the same number every time, right? You have a common difference. And then geometric sequence, it's a sequence of numbers, which remember is just a list separated by commas. A sequence of numbers where the ratio of consecutive terms is constant. Ratio of consecutive terms is constant. Yesterday, it was not the ratio of consecutive terms, it was the difference, right? There was a common difference between consecutive terms. The next term minus the previous term was always the same number in an arithmetic sequence. In a geometric sequence, it's the next term divided by the previous term. That will always be the same, the ratio. Okay, ratio. Okay, so let's take a look at an example of this real quick. And these get out of hand real fast, but for the most part because of the fact that we're multiplying here. Okay. Is this a arithmetic sequence? No. How do we know? Right, we're not adding the same number every time. From 2 to 6, we're adding 4. 6 to 18, we're adding 12. 18 to 54, we're adding 36. Okay, so not an arithmetic sequence, but is it geometric, right? So what's the ratio here between the next term and the previous term? So the common ratio is 6 over 2, which is 3, which is also equal to 18 over 6, which is also equal to 54 over 18, right? So you see you take the next term divided by the previous term, and you get that ratio, that common ratio of 3. So the common ratio then we have is 3. And I just generically a sub n plus 1 over a sub n. Okay. Always the next term divided by the previous term. Okay. So this is geometric. Okay. To find the nth term, so remember yesterday we talked about how to find the nth term of an arithmetic sequence. Because yesterday we were repeatedly adding the same number over and over again, we ended up just using what mathematical operation? When you add the same number over and over again, we can just use what mathematical operation? Multiplication, right? Well, here we're multiplying by the same number over and over again, so what kind of idea should we use now? Exponents, right? Exponents show repeated multiplication. So the nth term okay, of a particular geometric series will be equal to the first term, times the common ratio to the n minus 1 power there. Okay? So for whichever nth term you want, you're going to multiply, you're going to have a certain, exponent of that common ratio, certain power of the common ratio, and then times your first term, and that'll get you to wherever you need to on your nth term. So again, that's the nth term. That's the first term. Common ratio. And this is the number of the term. Okay. So let's write out the first 5 terms of the sequence given a sub 1 is 3 and r equals 2. This is an example here. Okay. So, where should we start our sequence? With 3, right? A sub 1, it's 3. Okay. What will our next term have to be? What's a sub 2? 6, yeah, just times 2 there. Okay? And then 12, 24, 48, and we're done, right? Because all we want is the first 5 terms. So there's 3, 4, 5 like that. Okay, question?
Do we always have to put like a sub 1, a sub 2?
I'm doing that just for your own kind of edification right now, just so you can see, associate, when you see those a sub something, it's associated with a particular term in the sequence. Not necessary to do that. It's just for your own kind of benefit to associate those things together. Okay. The direction don't ask here, but let's go ahead and just write the formula for the nth term too. So the nth term here, right? Remember, it's the first term, so that's going to be 3 times our common ratio is what here? 2, and it's to the n minus 1 power. Okay? And so there's our kind of formula for the nth term, whatever other nth term you want. Or actually, I guess it might make more sense to do it this way, with what I was writing there. There we go, like that. That makes more sense. With how I was writing it, it's more consistent. Okay? Questions on any of that? All right. Here's one for y'all to try then. And then we'll get into the series. Find the 15th term of a geometric sequence whose first term is 20 and second term, one second here, excuse me, is 21. Okay? And the 15th term of a geometric sequence whose first term is 20 and whose second term is 21. Okay? Couple different ways to do this. Cooper, have a seat.
I'm so lost.
Okay? We'll get you going here, bud. All right, so let's talk about this then, Cooper, right? So do you have any idea where to start here?
Not particularly.
Okay, so we have a formula we just talked about how to find the nth term of a geometric series.
Okay. So
Right?
A sub 15.
So, right, we have the formula right up here on the board for you. A sub n equals a sub 1 times r to the n minus 1. Okay? We're trying to find, and I got my answer there, so I gotta hide it now. We're trying to find the 15th term. Okay, so that means a sub 15 is what we want there.
Equals 20.
Equals 20.
I don't know after that.
Right, what's the common ratio? How can we figure it out? 1. So remember that the common ratio, it's the ratio of the next term divided by the previous term. So 21 divided by 20, that's 1.05 when you simplify that
Okay.
as a decimal. So 1.05 is our ratio there. You could also use 21 over 20. That's fine. You can use that if you want. Say that's your common ratio. Okay. To the n is 15 minus 1. So we'll have to do 14 really, ultimately there. Okay, and so we end up with, whoops, I forgot to fill in the rest here. So a sub 15 is 20 times 1.05 to the 15 minus 1, which is going to be 39. I'm going to approximate this because it's a mess. 39.599, I'll round it to. And I froze it. Sorry about that. There you go. Okay. Okay. Does it make some more sense now, Cooper?
Yeah.
All right. So it's a matter of, kind of understanding the pattern here. First of all, we're told it's geometric, so that means we know the first term, so really it's a matter of figuring out common ratio, right? Just like for an arithmetic sequence, you're going to figure out that common difference. Okay, so common ratio. And common ratio is always a next term divided by a previous term. Next divided by previous.
Okay. And it doesn't matter what you have a say, it doesn't matter what you do.
If I gave you the third and the fourth term, you do the same thing. The fourth term divided by the third term, get your common ratio, and then you have to go kind of backwards to get the first term and stuff like that. So, okay, questions on any of that? We're ready to move on to series. All right, ready to move on to series. Here we go. So then a geometric series well, there's two formulas for geometric series that we're going to learn. We're going to learn how to find the sum of a finite number of terms in a geometric series. Okay, I don't have a neat story for this one. You might debate about whether my first story was neat, but I think it is. We'll just have to agree to disagree, I guess. Okay, that's our formula. The sum is equal to the first term, okay, common ratio for r, of course, and then n is the number of terms. Okay. So that's the finite geometric series formula there. Okay. That's if you are going to add up a finite, right, a limited number of terms in the geometric series. So we'll do 2 here. We'll just say our directions here are to evaluate, and we'll go back to our old friend sigma notation that we all love. Okay. Thank you. Thank you. So, in order to find our sum, in order to use our formula here, we need to know a few things. For example, we need to know what the first term is. What is the first term of this series going to be? 0.3 to the first power, right? To the first power, right? Because we start at n equals 1. So our first term here, our sum is going to be then 0.3 to the 1, or just 0.3, times 1 minus. What's our common ratio going to be here? You might be able to determine it just by looking at this. We're repeatedly multiplying by more 3's, right? Every time I go up, my next power of n will be n equals 2. It'll be 0.3 to the 2. I just multiply by another 0.3, right? So yes, my common ratio here is just 0.3, okay? And we're trying to find the sum of how many terms? 8 terms, right? 8 terms. First 8 terms there. Okay? Over 1 minus, again, that 0.3. Okay? So this quantity will give us what the sum of those first 8 terms is. So let's go ahead and do that. Now, this is where it gets a little bit tricky to type into your calculator, okay? Students have difficulty with typing this in because of all the little pieces. So just be careful when you're typing this in your calculator here. I'll try and help show you what I like to do. So what I recommend is use parentheses here. So for example, parentheses 1 minus 0.3 to the 8th. Okay, so there's my numerator. I'm holding off on the 0.3 on the front outside there, okay? Divide by 1 minus 0.3. Okay? So there's just that big set of parentheses right there that I just did. And we'll multiply our final answer by 0.3 once again. We get this. All right, I don't know if it'll give me a nice, yeah, it won't convert that to a fraction form. Okay. So again, I kind of like to do the big fraction, the big parentheses set there first, then multiply by that 0.3 out front, and you get that. Okay, and I'm just going to go ahead and write out the whole thing. Okay. So there's our sum of the first 8 terms. Okay. Questions on that? Again, if you have some trouble, feel free to write out the first couple terms there. You know, or you can even write them out, 0.3. I think this will be what, 0.09, and this will be like 0.027. You get the idea there. So you can write out those first couple terms if you need to, just kind of bless you, help you out and stuff like that. Okay. Let's try another one here. How about you guys try this one here? Okay, you have the calculator? Boom. Boom. I've got one to spare here. I'll get you one in a second. If you'd like. That's fine. I can also give you one to try, though. So here's one for you to try. Okay, find that sum. Find that sum. Okay, find that sum, please.
So what are you giving to it?
Okay, so your first term, I would suggest writing out your first couple terms here. Using this, so like equals, and what's your first term going to be? So when n is 1, 1 minus 1 is 0. What's 3 to the 0? Times 4. So equals 4. So 4 is your first term. So the next term, plug it in 2. 2 minus 1 is 1. 3 to the 1, 3 times 4, 12. It will be 4, 12, so on and so forth. Okay? Write out your first couple terms if you need to. That's okay. You do it though. You see yourself making errors and stuff. Yeah.
Wait,
It's right?
Yeah, that's right. What? Okay. There's your answer. 1 million. 1 million. 62,808.
Hey, Mr. Wood, do you know
Oh, because I did see 11.
I do.
what is it?
That's none ya. None ya dang business.
Ryan Miller just said that.
Guess what mine
It's true. She speaks the truth.
Really?
It
You
is.
just checked.
I did. All right. Now, let's take a look at adding up an infinite number of things. Yes. So, with arithmetic series, let's go back to yesterday. Arithmetic series, we already established, right? If you try to add up an infinite number of things whose common difference is the same, you're going to get either infinity or negative infinity, depending on whether your your common difference is positive or your common difference is negative. For geometric, though, there are scenarios where if you add up an infinite number of things, you will get a finite number. Now, what kind of characteristic do you think is going to be necessary for that to be so for a geometric series? Compare maybe these two sums that we just did here. One sum was this. One sum was this. Okay, now granted, they were both finite, but imagine extending those to an infinite number of terms that we add up. Okay, so not from 1 to 8, but from 1 to infinity. Not from 1 to 12, but from 1 to infinity here. What kind of characteristic do you think is going to be necessary in order for an infinite number of things in the geometric series to add up to a finite number? Any ideas? Yeah, Parker, what do you say?
Ratio less than 1.
A ratio less than 1. Exactly right. Yeah, exactly right. Because why? You want to kind of try and explain why you think it's got to be that?
Like you add on stuff that gets smaller and smaller every time, so you can like approximate it to like it's going to be at this at one point before you just add it on basically nothing.
Mm-hmm. Right. So if we continually multiply by a number between 0 and 1, right, our number that we're adding on every time is going to diminish. And it's going to diminish so much that it's going to become essentially insignificant as you go to infinity, and so we will come up with a finite sum. As opposed to a number here greater than 1, this sum will continue to grow and grow and grow and grow and grow without bound. It will never reach a finite number because it's just going to get bigger and bigger and bigger, right? You can see right here, this is after 12 terms, we're already at 1 million. Okay? But this one after 8 terms, we're at this very small number here. And so yes, that is exactly what our stipulation here. So for a infinite geometric series, the sum will be the first term divided by 1 minus your common ratio, like that. Only when absolute value of r is less than 1. This is crucial. Okay. If I give you a series and I ask what is the sum of this infinite geometric series, do not automatically assume you use this formula. Okay? So again, if I ask you to find the sum of an infinite geometric series, do not automatically go to use this formula. We only use this formula when our common ratio is less than 1, or the absolute value of our common ratio is less than 1, because you can do negatives as well. Okay? You can do negatives as well. All right? This formula, you're going to see this later on in calculus ABBC, should you move on to calculus ABBC. It's something that actually shows up like way late into BC. You'll see it again. Okay, we'll be using it then too, okay, with some other stuff. But for right now, it's pretty important. All right, so let's just do this real quick. So we'll find the sum of let's find this infinite sum here. And we'll go ahead and assume it's geometric. Okay. Notice it just says dot, dot, dot. We're continuing on. That indicates we're continuing on infinitely here. So what information are we going to need in order to find this infinite sum? Okay. What do we need to find here? Common ratio, right? We already have a sub 1, so we can already say that the sum is going to be 500, that's our first term, over 1 minus. We've got to find that common ratio. How do we find the common ratio again? What can we divide? 300 and the 500, 180 and the 300, whatever you want. So I'll go ahead and just do the 300 over the 500. That's easy. 3/5. Okay. What's 1 minus 3/5? 2/5. Okay, and instead of dividing by 2/5, I'll take 500 and multiply by 5/2. Okay, 500 over 1 times 5 is 2,500. 2,500 divided by 2, 1,250. Okay, and so in other words, starting at 500, adding 300, then 180, then 3/5 of that number, then adding 3/5 of that number, then adding 3/5 of that number, on to infinity, an infinite list of numbers added up. Your final sum will approach that 1,250 and go no higher than that. Go no higher. Okay? Pretty interesting. If you don't believe me and you want to kind of check that with your calculator, you could use your finite geometric series formula, put the 500 in here, all right, put in 3/5 for your r's there, and then put x in for your variable. And then you can try just typing in larger and larger numbers for x and see that that sum is going to approach 1,250 and will never go over that. Okay? It's pretty crazy. Adding up an infinite number of things and reaching a finite number. Okay? So, questions on any of that? All right. If not, then we'll have you get started on the assignment. All right. And again, highly recommend you get started on it right now. Give you time, and it's going to be really helpful for you to practice this stuff. Okay. Especially if you found some difficulty on the homework or in class. So it's going to be 667, page 667, numbers 7 to 19, 23, 35, 37, 45, 49, 67, 77, 83, and then 93 to 101.
This is a long one, Mr. Quiz.
It's just a lot of like spread out numbers, so. Okay.
Right.
Well, it's not.
I need one machine.
Why don't you keep talking?
Because I don't hear him ever.
Yes,
My
you
grade's
did.
a 90.
I didn't know 90.